Okay, we're going to start on 12.3, which is the so-called dot product. So this is going to be a way to get a scalar quantity from two vectors. So now recall that you really can't do, there's no, I'll call it the usual multiplication of vectors. But you can take what's called the dot product. So let's go ahead and define the dot product. So given a vector A, which is A1, A2, A3, and a vector B, which is B1, B2, B3, their dot product is given by, so we'll denote it by A and then dot B. So now this dot product, this dot is no longer a multiplication for the remainder of this course. When we see vectors in a dot, it's going to be this dot product. So what is it defined as? It's defined as multiply the coordinates, corresponding first coordinates, and then add. Multiply the second coordinates, add, and then multiply the third coordinates. So this is the so-called dot product. It has a lot of good properties, but before we do any of the properties and such, let's do a simple example. So let's take A to be 1, 2, -3, and B to be 0, 1, say, I don't know, pi. Then A dot B is the first coordinate of A times the first coordinate of B, and I guess maybe let me not use dots for multiplication just here, let me use parentheses, plus 2 times 1, and then plus -3 times pi, and so we simply get 2 minus 3 pi. So notice we started with two vectors, and we ended up with a scalar quantity. Okay, so what are a few basic properties? First of all, note that here, I'm not going to list all of them, they're in your book, but I'm going to list a few of them. One important property is A dot B is equal to B dot A. So this property is called the commutative property. Okay. Another important property is that, so if you have A and you dot it with the sum of two vectors, B and C, this is A dot B plus A dot C. Okay, so this is called a distributive property. And I'm not gonna prove these, they're fairly straightforward. You can see here that if you dotted it in the opposite order, you would get the same thing here. 0 times 1 plus 1 times 2 plus pi times -3 for B dot A. Okay. There is, so the third property, this one is, I'm going to put a little star. We're going to do this, we're going to prove this one. So we're going to show that A dot A, the dot product of a vector with itself, is the length of the vector squared. So this is an important property. So let's prove that. It's proof of C. So again, let's assume that the vector A is A1, A2, A3, so that A dot A is A1 times A1 plus A2 times A2 plus A3 times A3, which is A1 squared plus A2 squared plus A3 squared. On the other hand, the length of the vector A, or well, so what's called the norm, you might hear me saying the norm of the vector, the same thing as the length of the vector. This is the square root of A1 squared plus A2 squared plus A3 squared, and hence our guy above here, this is exactly the length of A squared. Okay, so this shows that the dot product of a vector with itself is the square of the length of the vector. Okay, so I'll summarize again. So hence A dot A is the length of A squared. Okay, let's what we're going to show now. So this is, let's call this a little theorem. And this is, so given a vector A and a vector B, A dot B is equal to the length of A, the length of B, times the cosine of theta, where theta is the angle between A and B. So let me just draw a picture of what this is actually saying. So I'm just going to draw it in the plane. You can imagine that these are sitting somewhere in space, but you can imagine that these vectors, well, even if they're lying in R3, which they are, we're going to assume they are, so this is maybe a little remark that you can think about, and this is how the theta is defined. There is a unique plane containing any two non-zero vectors. Okay, so this, let me just draw something in R3. Try to anyways. Here's A, and here's B somewhere sitting over here. If you sort of think of completing the parallelogram here, if I make a little parallelogram out of this with these two vectors, that's a square, and that square can extend to this unique, that's that unique plane. If you extend it out, you'll get a plane. So in that plane is where our angle theta is sitting. Okay, so our angle theta, where is it sort of, how do you find that, or how do you locate that? Well, first you locate the unique plane containing these two non-zero vectors. In that plane you draw this angle. So that's how the angle is drawn, but for simplicity let's just draw it right here on the left, and we know that this vector here is the vector A minus B, right? So this is from an earlier earlier discussion. So, well, and we're not really going to be concerned about, we're going to be concerned about the length of these. So what we're going to show, so our proof, we're going to prove the theorem above, prove the theorem, which says, again, that A dot B is equal to the length of A times the length of B cosine of theta. Now what we're going to use, is the law of cosines. Now what does it say? Well, it says that the length of A minus B here, that side squared, is equal to A squared plus B squared minus 2 times A times B times the cosine of theta. This is the law of cosines. The side opposite to the angle. So this is this is the square of the length of the side that's opposite of theta. That's equal to the sum of the squares of the other two sides minus 2 times AB cosine of theta. Okay, so this is what we're going to use to do this problem. And so now, well, where do we go from here? Recall that A squared plus B squared, so remainder, let me just slide down a bit here. So we have that this here, so notice A minus B, this is A minus B dot A minus B, right? The norm squared is the dot product of the vector with itself. So this uses the, this is equal to that. And that's again because any vector dotted to itself is equal to the length of the vector squared. So this is equal to A dot A plus B dot B minus 2 length of A, length of B, cosine of theta. Okay, and now what we're going to do is we're going to use the distributive property. So from here, we're going to dot, so this is, we're going to use from here, let me draw a little line here, we're going to use the distributive property, and this side becomes A dot A minus A dot B minus B dot A plus B dot B is equal to everything here on the right hand side, A dot A plus B dot B minus 2 length of A, length of B, cosine of theta. And so now we can cancel, so the A dot A with the A dot A, B dot B with the B dot B, and by commutativity, this is minus A dot B minus A dot B is equal to minus 2 length of A, length of B, cosine of theta. And so we have minus 2 times A dot B is equal to minus 2 length of A, length of B, cosine theta. And so dividing by -2, we get our results. Okay. So this is an important result. And what we'll do in the next video is we'll do some applications. So in the next video, we'll apply this formula. Okay, that's it for now.